does. Cool. Thanks for having me here. I'm very happy to be able to talk about the LibraBFT protocol, which is the protocol that we have developed for the Libra blockchain. This is a joint work with many people, obviously. Some of them from the research group are in this room: Dalia Malki, Jordan Ezis, Alberto Sonino. And before I start, I would say I can make a test, maybe. If you were to choose a BFT consensus protocol for a major blockchain, and let's say you're a CTO with a background in science, but not a specialist, what is the one thing you will ask about this protocol? Right. How much? How much are you going to pay the person that? Oh, that's interesting. I should remember that. All right. Okay. So I think maybe one thing you can ask is like, you'd like to have a proof of safety of the protocol that you actually understand, or you think you understand. Okay. So we were lucky to meet the authors of the HotStuff protocol early on in our project, and I think it's fair to say that's the one thing that we really like about this protocol, that we had the sense that we kind of understand the proof of safety. It was kind of concise, on top of using like a very strong model, eventually synchronous, and then we also felt like, okay, the protocol looks like really efficient. We got this nice linearity, responsiveness, which I will talk about later, in pipelining. And so we're like, okay, well, this is it. We just need to implement it. In theory, everything is done. But maybe the problem is there's always a bit of difference between theory and practice, although in theory there's none. So, and so I shut down everything? All right. So we started working on, and so here the catch is that the pacemaker, I mean, the nice thing about HotStuff is you can really prove safety and to some extent prove liveness, abstracting away a big chunk of the leader election. And so that's the part that was missing. And so this is the reason why I'm here today, is because in LibraBFT, we made precise what we need to achieve liveness. And in fact, we want it to be really built in the protocol. Because, I mean, like if you go to an engineering team, you say, hey, thanks for building the protocol. Now you need to build another protocol for the election. They tend to not like it so much. They think like when they combine everything, it's going to be hard to debug everything. So we really want to combine everything, which is also kind of standard for many blockchain protocols. And so in this talk, I will start by, I'm sure many of you know the HotStuff protocol, but I'm going to revisit nonetheless using LibraBFT notations. And so you might notice some differences here and there. And then I'm going to go into the main topic of the talk, which is the round synchronization that we developed for LibraBFT. And in fact, I'm going to present the version 1 and version 2, and version 2 being the most interesting, I think. And if I have time at the end, I will try to conclude with a number of general comments on the model we're using for, or everybody actually is using for state machine replication. Okay, so I'm going to start with the core HotStuff protocol within LibraBFT. So how does it work? So as you know, those are leader-based protocol. So let's say we have a round number, and the leader is deduced from the round number. Okay. What we expect from a leader is to, and I'm going to actually use the nice the diagram. So what you expect from a leader is to gather whatever user transactions you want to execute in the blockchain, put that into something we call a command, put the command into a block, sign it, broadcast the block, and to everybody in the validator set. And what you hope is that everybody is going to reply. They're going to carry on a number of verifications, and if they like your block, they're going to reply with a vote. And once you have a quorum of votes, you can aggregate them and create what we call a quorum certificate. And then in LibraBFT, the leader would simply rebroadcast the quorum certificate, and that concludes the round of this leader. Okay. So what's interesting with HotStuff, it's also there's an extra data structure in particular. So we expect a vote to contain the hash of a block. We expect a quorum certificate to contain, to be linked to the block that is actually certified. But in LibraBFT, you also expect the blocks to contain a hash with the quorum certificate of a previous block. So this gives a structure of chain that is interesting. And you can see that, for instance, if we agree on the block B2, well, we have to agree on everything that is before. So, and this was well explained in the presentation also earlier. There's the idea of pipelining, that this certification here certifies not only B2, but the certification of B1. So you see where I'm going here. And obviously we want the round to be increasing along the chain. That's part of the condition for validity that is checked when you're about to vote for a block. So you see where I'm going here. Now we can, in fact, very easily state a commit rule, which is the following. If I know a chain that ends with 3 QCs, and the round numbers happens to be contiguous, so let's say 1, 2, 3 in this example, then I can look at the first block of my commit rule and say, okay, well, this thing is committed. But as I mentioned before, what's nice, since we are chaining everything, not only I commit this block, but I commit everything, any other block previously not committed that would appear earlier in the chain and in the right order, as you imagine. Okay, so sorry. Okay, so now why do we care about continuous rounds? So this is going to appear in the proof of safety, but I guess another question is like, oh, why is it the case that sometimes you'd have non-contiguous rounds? And this, in fact, this is related. This happens when a leader doesn't do his job, and that's kind of the only thing we need to know about view changes in HotStuff. There is no view change, right? This is just a gap in the round number. So I just explained the commit rule. Now we'd like to know whether this actually works, whether this enforces safety in terms of the absence of fork in the protocol. And so safety comes at a price. The nodes have to, in addition to the well-formedness of the blocks, the nodes have to do a few verifications that are called safety rules. So, and that involves tracking 2 integers, 2 round numbers. So nodes must remember, for any block they voted for, they must remember the round, and they must remember the round of the grandparent of that block, okay? So you need to remember the maximum number for those 2 values. And every time you're going to vote for a block, you check that the round of the block is greater, so that the round of any previously voted block, and you need to verify the round of the parent of the block is greater or equal than the round of any grandparent of voted block in the past. And that's not a typo. This is really parent and grandparent here, although it may seem mysterious. And so the nice thing with those 2 rules is that's kind of all you need to know to prove the safety of HotStuff. So I actually made the exercise to gather everything you need in one slide. Probably I don't have time to go over the proof. This is the main lemma that says if I have a block with a QC at a higher or equal round than the block I just committed, then I know there's a path. There's a chain that goes from the commit to my block. Okay, and so why does it prove safety? Well, this thing, so first, this diagram lives in the union of everything the nodes know. Okay, so this could be a commit in one node. This could be a block that is about to be committed somewhere else. And what I'm saying is, oh, wait, there's a chain between this one and this one. And so I just showed that there's a linear sequence between all the commits across the network, okay? So, and once again, the nice thing here is really that this slide is possible. You can have one slide for the safety proof of HotStuff and LibraBFT, okay? Okay, now, if we look just a little bit closer at what's happening in terms of storage and communication. So we have those chains of blocks, and it might seem like, oh, we find ourselves having to synchronize a tree of blocks and QCs over the network. But actually, in practice, you can show you need only to remember the highest commit rule you ever saw and the chain that precedes the highest QC you ever saw. So that's only 2 chains, and they are mostly equal. Also, when everything is good, then you have, in fact, only one chain, and you can show that the communication, at least the number of messages, is linear in the happy case. And if you're using threshold signature, that's strictly linear in terms of network complexity. Okay. All right, so that's for the safety core of HotStuff. Are there any questions so far? Everything is completely standard, maybe? Okay. How about liveness? So for a QC, so we want to create a commit, right? So for a QC to be created, so all the honest nodes needs to be to agree on the round number. Otherwise, they will be surprised to see this block being created by somebody they don't expect. The leader must be honest to propose, and all the nodes must vote for the proposed block, right? So that's this stage we're talking about, the voting. So why is it a concern that all the nodes need to vote? Well, as I just explained, for safety, we just added these two constraints, okay? So the question is, like, as a leader, how do I propose my block to make sure that people can actually vote for it? Meaning that these two constraints are going to pass for every other validator. And I think it's fair to say that one of the main contributions of HotStuff and distinctive point is that to propose a block, you don't need to wait a fixed delay. You just need to count a number of samples, n-f rounds of QC given to you by people that just entered the round. Okay, so once again, and let's say in Tendermint, for instance, you would only wait for a fixed delay and then you propose. Okay, so in HotStuff, you wait for n-f nodes to join your round and tell you what is their highest QC round. Okay, when that happens, you take the highest number, and that's where you need to extend the chain. And if you do that, you are guaranteed that people are going to be able to vote for your proposal, which means that solves the problem we had for the liveness. So what's left here is the two other points. The honest node needs to agree on the round number, and the leader must be honest. The second point means, in particular, if the leader is dishonest, we need to be able to skip that round in a timely manner, hopefully. This whole problem is called round synchronization, or so leader election. Okay, so in a very simplified way, so we'd like to know what happens between the red dotted line that is actually making nodes switch to the next round, okay? So once again, if we take the point of view of like a practitioner, so we're starting from a network that is very nice. You know, you have really, it seems like you really have the minimal amount of messages in there that is able to guarantee safety. And now we're going to add stuff to it. So we would like to add the minimum amount of overhead, okay? Also, if we add something, we'd like to know that actually it's efficient. So we'd like to know that even if you have Byzantine nodes in the system and the network is scheduling the messages in the wrong order subject to the delta delay after GST, we'd like to know that still the commit latency is fine. So like I said, in HotStuff, round synchronization is delegated to an external protocol. Actually, recently we were studying what this external protocol could look like in a separate line of work. In Tendermint, the protocol includes round synchronization and is using timeouts and probabilistic gossip. So the natural thing to do that we did in LibraBFTv1 was to try to make something similar work, okay? And in LibraBFT2, we thought, okay, it works, but we don't really like probabilistic gossip because it's a non-linear amount of messages, including in the best cases. Also, you know, like introduce probabilistic behavior in the system, so it's a little more difficult to debug what's going on when you look at the exchanges between the nodes. So, and this is the result of, and so LibraBFT is the result of these attempts. Okay. So now I'm going to introduce, okay, how the round synchronization works in LibraBFT. So the first idea, and it's still pretty reasonable, I would say. we're going to add the maximum duration to every round number. After the maximal duration is reached, every node creates a timeout object and broadcasts it, okay? Now, when do you move to the next round? You move to the next round when you have seen a quorum of votes, a QC, as before, or when you have seen a quorum of timeouts, which we call a timeout certificate, okay? So here we see that like leader, the last node was supposed to be the leader. The leader doesn't do anything. Everybody's starting broadcasting timeouts. And after receiving their own timeout plus 2 more, they switch to the next round. And this node apparently was the leader. And ideally, we'd like this node to immediately broadcast a new proposal, okay? So that would be a solution with like almost no overhead. A second idea, while we're at it, since we are already communicating, we're gonna, when we do that, and that's also related to the notion of chain. Since we want to communicate entire chains with people, every time there's an arrow in this diagram, what it means is I'm telling you a summary of everything I have, and then you ask me what you're missing. Okay, so that's the second idea that could help for liveness. Okay, and it's still pretty natural. And so the question now is, all right, are we good to go? Is this protocol BFT live? Right? And so the answer is no, not quite. First, there is something I told you that I haven't really implemented yet. I told you, hey, it's awesome. We are responsive because we can propose after receiving n-f message from the people that just joined our round. Okay, but I haven't implemented that. So in fact, what could happen is that everybody that joins my round, if I'm leader number 3, everybody needs to talk to me to say, hey, I just joined your round, and this is my highest QC, by the way. But then we see that we introduce some latency here because now as the leader of round 3, not only, so after I join my round, I need to count the number of red arrows coming in. And so that introduces a little bit of delay. So a question would be like, okay, can we avoid that? And then a second problem is what if a leader is dishonest, it doesn't really broadcast the QC correctly. So what could happen is that you have a leader that only broadcasts the QC to a subset of f+1 nodes, gather f+1 votes, then use f malicious keys to create a QC, and then you take this QC and you show it only to the people you were talking to in first place, which means you have f nodes that haven't heard about your new QC, so they're stuck at the previous round. And then if the next leader is dishonest, you can repeat. So that's not necessarily a problem because, of course, eventually you're going to have a honest leader. But it's kind of bad for if you are really into analyzing the latency of the system very precisely. And also a good question to ask. So in LibraBFTv2, by the way, this is solved entirely by using probabilistic gossip. So there's no way for somebody to censor, to selectively disclose a QC because everybody is resharing everything. So in LibraBFTv2, we'd like to remove the gossip. Okay, so we are going to have some kind of problem like this for some time. So the question we can ask ourselves is, okay, as long as you have dishonest leaders, they can forget a part of the network. But the next leader that is honest, can this leader do a good job nonetheless? Okay, that's if you are really into having a system that goes back very quickly on track after a problem, that's a nice property to have. So the solution that we developed that I call fast proposal is a tweak, a very simple tweak on the definition of the protocol, of the version 1 protocol. And so I'll tell you what we obtain before telling you what is the modification. So what we obtain is that I can propose a block as soon as I receive one of those green arrows. So if anybody in the system joins my round, they are going to send me a notification. First, they are going to convince me to join this round if I haven't already. And second, they are going to convince me to give me enough material so that I can propose a block right away. What is interesting with this as a byproduct is that when I propose a block, I'm also synchronizing the entire chain that is before that block, which means that I'm also completing the broadcast if needed and bringing everybody to my round. So the property is that if somebody joins a round after GST, if somebody joins the round at time t, by time t plus 2 delta, everybody else is at this round, okay? Okay, and the way you achieve that very quickly is you inject the highest QC round inside the timeout object, and you change the safety rule to prevent somebody from voting if they ever created a timeout for this round, okay? So when you do that, you can show that, in fact, the TC thing counts as n minus f samples of highest QC, so that's exactly what you need to propose, and that was also already the case for QC. All right. Okay, are we done yet? Well, not quite, because the same problem with incomplete broadcasts that we just discussed with the QCs, we can have it with TCs. So what could happen is that you have a leader at round K, let's say it's slow, and the next one doesn't want to help, is dishonest. So the attacker waits for f plus 1 honest node to time out at the round K, okay? And then takes the f plus 1 and completes that into a quorum again, and that gives the attacker a TC, and they can do whatever they want with the TC. And so what they're going to do is to give it to people who haven't timed out yet at this round. And since this is going to bring, in this case, the node number 2 to the round, to the next round. And so it means that in the system, except for the TC that the attacker just created, there is not enough timeouts for the honest nodes to move to the next round yet, okay? So at this point, you have one node that is at round 3. Everybody else, this node was malicious. Let's say it's not responding. So everybody is going to wait at round 2. They have already timed out. So from their point of view, their job is done. They are waiting for a TC to happen, and the TC is not happening because this node is already at the next round. Okay. So what is going to happen is eventually this node is going to time out at the next round, and then it's going to propagate the Byzantine TC. But the whole thing took intuitively twice as much time as before. When we were using gossiping, the whole thing was taking only duration k. Now it takes duration k plus 1. And so you see that this node will only time out at round 3 after 3 periods of timeouts. And so the question is, can we do better? We see that removing gossiping is degrading, in a way, the worst case latency of our protocol. Can we fix that? So the solution, the solution that we developed is the following. So, and we try not to ruin the linearity of the protocol in the happy case. So what's going to happen is that a node, if after timeout nothing happens yet, it's going to start pulling data from everybody at a lambda duration k interval. So concretely in our case, you see that we have a node that knows the next TC, and the other nodes don't know it. After a while, they have already timed out. After a while, they are going to query everybody, including the node that had the missing information, which is going to bring them to the next round much sooner than before. Okay, and so this means that the next round is going to fail also sooner than before. And so we can show that in this case, to summarize, a bad leader can only cause us a delay 1 plus lambda duration k, which is, if lambda is small, it's a trade-off. We can choose the lambda to be arbitrarily small. It is close enough to duration k, which was the ideal case that we had in the case of gossiping. All right, so how are we done with liveness yet? Almost. So for a commit to happen, we need 3 QCs in a row to be created. In the report, so we discussed the consequence of incomplete broadcast, or we deal with the consequence of incomplete broadcast for commit rules as well. that introduced one more mechanism that is similar to the one I just described, just based on commits instead of rounds. And that introduced this constant I. The reason I'm talking about this is because now I want just to show you a glimpse of the final latency bound for LibraBFTv2. So the theorem that you obtain after this perhaps painfully detailed analysis is that you really know under BFT assumptions after GST how much time you need to wait for the next commit. The way it works is you look at the highest round between honest nodes. You find out what is the lowest n such that 3 leaders in a row are consecutive and the timeout is large enough. And then this is the formula. You know that this is how much time you need to wait, and you are guaranteed that a commit will happen by this time, no matter what. No matter how the network is rescheduling, reordering the messages, as long as it's still synchronous. Okay, delta is the synchronous, the bound on message delays. Okay, so to conclude on LibraBFTv2, so I introduced some liveness mechanisms that enabled us, allowed us to remove probabilistic gossip, which means that we are optimistically linear, linear network complexity in the case of in the happy path. And I showed that the impact on BFT latency, the formula before, is still limited. In the report, you have more details about the way reconfigurations are handled and the way we can make leader function and duration function depend on the latest commit. If you want to reseed the leader election, for instance, with VRFs. I should mention that the whole of this, there's a reference implementation, like a minimal reference implementation that is now available on GitHub. This is the one that was quoted in the report from the beginning. And stay tuned, so that this is not the end of the story. There will be future versions of the protocol. And if I have maybe one more or couple of more minutes. So just a few generic remarks about security. So we work in the eventually synchronous model. I think it's a strong model, so good. However, very often in the academia, the results are only about eventual liveness. And so for a practical point of view, it doesn't really tell you when you are going to commit. There are perhaps too few results about bounded delay. And so this is one more of them. Perhaps by analogy with the concrete security reduction in cryptography, this is going to become a more mainstream. Other slightly, I'm going some, I kept all my controversial statements for the end of the talk, as you can see. So in the paper, we intentionally deviated from the usual definition of eventual synchrony, so by allowing messages to be lost during periods of asynchrony, which I think is more realistic, because if you don't want this, you will need to have unlimited buffer during periods of asynchrony to make sure that you never lose the messages. There's also the question of whether you allow malicious, honest nodes to crash and restart. Do they count as malicious if they do that during the period of asynchrony? I think it's fine. Another interesting question that was also discussed this week is like, do we really believe in this BFT assumption, like 1/3 of malicious nodes? So if we are in a permission model and you talk to engineers, when liveness is concerned, they think that actually 1/3 of malicious node is way too conservative. So in fact, that's kind of that was one of the motivation to aggressively optimize the network complexity in the happy path for LibraBFT. If node membership is open, then how do you know that F is smaller than 1/3 of the nodes? It's actually kind of reckless. So we try to, and this is still an open topic of research, obviously, but so we try to be future-proof by already discussing some ways to incentivize nodes in LibraBFT. And finally, this is my last slide. In the BFT model, we say that malicious nodes can deviate arbitrarily from the protocol, but usually it's still at a pretty high level of abstraction. What do we, I mean, if we are really serious about it, we would think that 1/3 of the nodes are trying to do horrible things including at a network level. For instance, they could try to inject packets that are going to to make the honest node go out of memory. And that would be a problem in practice, right? Or can the dishonest node force, along the same lines, if you inject a lot of amount of data in the network, can you in fact make the messages of the honest node behave asynchronously? If you do that, then you have no period of synchrony anymore, and the theorem, in fact, is not going to apply anymore. So that could be a practical problem that maybe we need more attention. And that concludes my talk. Thank you very much.
Any more questions before the break?
Do you have some immediate ideas how you can squeeze out more performance, get quicker synchronization of the GST, or do you think you are pretty much at the limit already?
Okay. So if you really care about latency, maybe you would be okay to pay n log n for communication for the broadcast, and maybe probabilistic gossip was okay in first place. Yeah, we will see. I mean, there are some. Anybody is welcome to look at the proofs and see. Oh, this is not tied here. Maybe.
It's complicated.
But so to be really, if you look at the, you can have some notion that the proofs are tied because some factors are actually what you need to weight. What you need to weight no matter what if you think that the nodes might be honest. So like you need to give the nodes a chance to perform their thing, and so you need to wait at least the amount of timeout it takes. So part of that is already tied.
You could also mention the paper we uploaded to the archive, the MIA.
Right. Oh well. So I mean, there's a yes. So I took your question as the happy path, but now in the unhappy path, we are still quadratic in the number of messages, which might be unfortunate if you think that quadratic number of messages is likely to saturate the network and bring asynchrony to you. Then you could actually create like a kind of asynchronous loop where you time out, that breaks the network, so you time out more, and that breaks the network. And so the work with Odenauer, Dalia, Spiegelman, and me, so it attempts to make the round synchronization strictly sub-quadratic in all cases. Perhaps using BDF also with a help at some point.
Okay, so we're only 10 minutes behind schedule.